Hello students, now we are doing our exercise examples of chapter number 5th. As you have been given that a vector needs three physical quantities for its specification for the Earth's magnetism. We have to name these three independent quantities. First of all, whenever we are doing such type of example, we have to just keep in mind some of the basic theoretical principles. Very first thing is that we are in a need of a declination. Next thing is called as angle of dip, or you can say that angle of inclination. And third thing we are in a need of is called as our uh, horizontal component. So these are the three basic things whenever we are in a need of basically three vector quantities. Next thing is that the angle of dip at a location in the southern India is about 18 degree. Would you expect the greater or smaller angle in Britain? As we have discussed in our theoretical portion, you can say that the further you are going away from your angle of dip, same would be increment in the angle of your dip. So you can say that the compared to the Earth's or southern India's comparison, the angle of a dip at Europe, or you can say that Britain, it would be around 78 degrees. So this is the far distance compared to the southern India. You can say that as farther you are going away from the angle of dip, your angle of dip's value is keep on increasing. If you made a map of a magnetic field lines in the Melbourne in Australia, would lines seem to go into the ground or come out of the ground? As we have discussed in our theoretical part, we have just said that let's say your earth's magnetic field, let's say this I'm just drawing that this is my earth and it's a magnetic field, and this is the magnetic north and magnetic south angle, or field lines are coming outside, so these are called as angle of inclination, and this is called as angle of d. So you can say that Malor is somehow over here, so there would be the increment into the terms of a magnetic field lines, so these are going outside, so it would be coming outside. In which direction would a compass free to move in the vertical plane point to the located right in the geomagnetic north or south? Whenever you are putting a magnet, it is moving freely first of all, and that is called as a freely horizontally. So this is the very initial thing. Whenever you are putting your compass box in a vertical plane, it is moving horizontally. Next part is that Earth's field. It is claim roughly approximately the field of due to the dipole of the magnetic dipole moment, and we have to just justify that magnitude of is would be in the nature of it or not. So let's say I'm just saying that my magnetic dipole moment is 8 cross 10 to the power 22 joules, and my distance or my radius of the earth is equals to 6.4 cross 10 to the power 6 meters, or you can say that 6400 kilometers. So this is the data I have. I want to find it out my magnetic field. So what I am doing is that initially I am putting that formula B is equals to mu 0 divided by 4 pi m divided by r cube or re cube. So you can get this value nearest to 0.3 Gauss. So it is validating that our fact that our magnetic field of our Earth, if your dipole moment is 8 cross 10 to the power 22 joule per Tesla, then our magnetic field is near to the zero point 0.3 Gauss. Our geologists claim that besides the main magnetic N and S pole, there are several local poles are like that. As we have discussed that because of the Earth's excavation, or you can say crest of the Earth is responsible, indirectly responsible for the magnetic field of the Earth. But at a different location due to the excavation or because of the increment or decrement of the material in the crest, there is a chances that there might be the change in Earth's surfaces or local poles. So yes, it is true. So yes, it is true. So such type of things are possible only because of that on the crest part of the Earth, different type of materials amount is something different. Next thing is that let's say we are doing that 5.2. The Earth's magnetic field varies from point to point in the so does it interchange with the time? Yes, it has taken billion amount of years. Let's say whichever magnetic field we are enjoying right now, the same amount of a magnetic field is not right now available, because previously it has changed through the billion of years ago, and that is why whichever magnetic field we are enjoying right now, it is because of that only. The Earth's core is known as the contained iron, or yet geologists do not regard as this as a source of Earth's magnetic field or magnetism. Why? The thing is that Earth's magnetic core contains, first of all, its a core contains molten part of iron, and molten iron is not a ferromagnetic material, so we cannot say that it is responsible for Earth's magnetism. The charge currents in the outer conducting regions of Earth's core are brought in this responsible for the Earth's magnetism. What might be the battery of such type of charges? So first of all, you can say that ionosphere contains so many numerous amount of charges. So this charges it is like a battery for that, and these charges are also you can say that magnetic field of the earth, and these charges are coming in contact with each other, and you can say northern lines or northern lights are observed. So this is the reason why you can say that what might be the battery, it is battery, this called as ionosphere. I can say Earth may be having even reversed to the direction of its field several times during the history of 4 to 5 billion years. How can geologists know about the Earth's field in such a distance past? You can say that initially Earth was separated from some, let's say, sun, or gradually it is cooled down. So because of that, there is a thick crust can be produced, and this crust has contributed a lot to produce a magnetic field of the Earth. The interstellar space has an extremely weak magnetic field of 10 to the power minus 12 Tesla. Can such weak field with any significant consequences? You can say that there would be a weak magnetic field can be bent of the charged particles. So you can say that charged particles in a circle, and maybe you can say that it might not be noticeable for the a large radius of the path. So with the reference to the gigantic interstellar spaces, the deflection can affect the passage of the charged particles. So you can say that our path of our charges has been changed significantly. Though these questions are only for your understanding or not for information, might be or might not be asked in the exam because it is only concerned with your knowledge. Now we are coming back to our actual course of examples. You have been given that your theta, that is called as initial angle, that is called as a 30 degrees, and you have magnetic field which is experienced by our object or bar magnet is called as 25 teslas, and torque experienced by it is called as a 4.5 cross 10 to the power 2 joules. We have to find it out magnetic dipole moment. So you are aware that the symbol of magnetic dipole moment is called as M. So you can say that first of all our formula is called as a tau is equals to m b sine theta. So I want to find it out my magnetic dipole moment. Sorry, I want to find it in my magnetic dipole moment. So m is equals to tau divided by b sine theta. I am putting these values of torque tau. Value of a torque is a 4.5 cross 10 to the power minus 2 divided by magnetic field is equals to 0.25, and sine 30 is equals to 1 by 2. So my magnetic dipole moment equals to 9 cross 10 to the power minus 2 divided by 25 is equals to, so my magnetic dipole moment equals to 0.36 joule per Tesla. So remember these units as well whenever you are solving such type of examples. Next example is that 5.4, a short bar magnet of a magnetic moment. So again you have been given that magnetic moment M is equals to 0.32 joule per Tesla. Is placed in a uniform magnetic field that is called as a B is equals to 0.15 Tesla. It is free to rotate in the plane of the field, which is oriented would be correspond to the first of all stable condition, and next is called as a unstable condition. So for the both these condition we have to find it out what is the potential energy of it. So we have to just first of all find it out potential energy. So our formula is equals to, for the potential energy is equals to mb cos theta. And again we have, this is also called as a minus mb cos theta. So for the potential at the stable condition, we have to just say that theta equals to 0, and here theta is equals to 180 degrees, or you can say that it is pi, because it is coming into the condition of unstable condition. So my values I'm placing over here, minus 0.32 multiply by 0.50, cos 0 is 1, so my answer would be negative, that is called as a 4.8 cross 10 to the power minus 2 times joule, because you are aware that whenever your values are like that and unit is called as a joule for the potential energy, you can also observe that the unit of a torque is also joule. Now u is equals to minus, that is called as a 0.32 cross 0.15 and cos pi. You are aware that cos pi is minus 1 minus minus plus, so you can directly place that 4.8 cross 10 to the power minus. So these are the examples which can be solved orally as well. Now exercise example number 5.5. In exercise example number 5.5, you have been given that a closely wound solenoid. Yes. In a such type of example, take a care that the number of turns per unit length is mentioned or not. If it is not mentioned, then quite easy for us. Now my solenoids having turns are 800. These are the number of turns. Now I have my magnetic current, which is called as a 3.A, which is only current responsible for magnetic field only. My area, and that is a 2.5 cross 10 to the power minus 4 meters square. So I want to find it out my magnetic moment. So you are aware about this formula, magnetic moment is called as NIA. So I am putting these values. Number of turns are 800. My current is equals to 3, and this would be 2.5 cross 10 to the power minus 4. So my magnetic dipole moment over here is called as a 0.6 joule per Tesla. So this is quite easy for you to just solve such type of examples. Now my exercise example number 5.6. 5.6 is associated with the 5.5's data, because here in a they have mentioned in exams, whenever they are asking such type of example, they are asking 5.5 and 5.6 combined. So you have been given that magnetic field over here. So your B is equals to 0.25 Teslas, and theta, which is called as a 30 degrees. We have found it out magnetic dipole moment in the from the previous example, that is called as a zero point 0.6 joule per Tesla. So that would be 0.6 joule per Tesla. We have to find it out magnitude of a torque. So my formula is equals to tau is equals to mb sine theta. You can orally do such type of example, because your theta is equals to 30, that would be 1 by 2, and this is called as a 0.25, this is 0.6, and this would be 1 by 2. So my torque is equals to, I'm doing this calculation of a 0.25, 0.6, that would be 7.5 cross 10 to the power minus 2. So these are the examples. Whenever you are putting such type of things together, it will be quite easy for you. You can just orally do such type of example. That would be 25 and 6, and that would be 35, 3 and 7.5. So these are the examples. Now exercise example number 5.7. And this is the one of the interesting example. You cannot say that such type of example is not to be asked. Only the thing is that why it is interesting. So because they have given you a different type of story for two things. Very first thing is that a bar magnet of a magnetic dipole moment, you have been given that m is equals to 1.5 joule per Tesla, and magnetic field B is equals to 0.22 Teslas. First of all, we have to find it out amount of work done. So what I am doing is that we have to find it out to work. Very first thing is in the direction of something, and next one in something direction. So I am doing that task with the work done. First of all, what is the amount of work required by an external torque turn into the magnet in the align in the magnetic moment normal to the field of direction. So first of all, my theta 1 is equals to initial angle, which remains as it is, and theta 2, as per my condition, it is called as a normal, or you can say that pi by 2, it is my final angle. So this would be pi by 2, it is a normal. So what I am doing is that u is equals to minus mb cos theta is my value. So I am putting that minus mb cos, that is called as a theta 2 cos theta 2 minus, sorry, what I am doing is that directly cos theta 2 and theta 1. So I am putting those things together. That would be cos theta 2 minus cos theta 1. So my formula would be work done equals to minus mb cos theta 2, that is called as a cos 90, minus cos 0. So I can have a minus mb cos 0, and that is called as a 1. So my work done is equals to minus 1.5, then 0.22 and minus 1. So my work done is equals to this much amount of joule, that is called as a 0.33 joules. Next thing is that we have now opposite to the direction. So my theta 1 is equals to 0 and theta 2 is equals to 180 degrees. So directly I'm putting these values in this expression, would be making my task easier. And then I can have a cos of 180 degrees minus cos 0. So you are aware that cos 180 is minus 1, cos 0 is again 1. That would be minus 1 and minus 1 minus 2. So my task would be minus mb, that is called as a twice times. So my answer would be 0.66 joules. Next thing is that what is the torque on the magnetic moment in the case 1 and 2. So first of all, we have to find it out. Torque is what? First of all, theta, which is called as a normal. So I can just use that normal, that is why 90 degrees, or you can say that pi by 2. So my value of a torque is equals to mb sine theta. So my value of m and b are 1.5 and 0.22. That is called as a 1.5 and 0.22, and sine 90 is 1. So I can have my answer equals to 0.33 joule. It is looking like the calculation which we have already done over here. That is 1.5 and 0.22, 0.33. Only the condition is that there was a minus 1 and minus sign over there, but here there would be no minus sign. Next thing is that my second thing, and that is called as my theta, which is called as a 180 degrees, and or you can say that value of this one. So my sine of 180 or sine 0 is equals to 0 value. So my torque will also becoming 0. So the interesting fact is that they have asked both those things together, which is a good thing actually. So whenever the examiner or paper setter is supposed to arrange example from this chapter, they're asking all those things together. So it would be quite easy for you to just evaluate all those things. Next is our example number 5.8, a closely wound solenoid of 2000 tons. So first of all, I'm putting that number of tons are 2000. So it is my tons. Next thing is that my cross sectional area is equals to 1.6 cross 10 to the power minus 4 meters square, and it is carrying the current that is called as a 4 amperes. So we have to find it out. Is suspended through the center, allowing it to turn into the horizontal plane. So what is a magnetic moment associated with the toroid? And they have also asked us that if my magnetic field is 7.5 cross 10 to the power minus 2 teslas with the angle theta, which is 30 degree. So by using this data, I have to use the torque or find out the torque, And using this data, first of all, they have just asked me that find it out dipole moment. Even though they haven't mentioned find it out magnetic dipole moment, there is no other way by passing through the magnetic dipole moment. You have to find it out magnetic dipole moment. Without that, it is not possible. So what I'm doing is that here in our data, which is directly available to us, is that they have just directly given us the area, and that is why our task is quite easy for us. So what I'm doing is that magnetic dipole moment is equals to, you are aware that that would be NIA. So that is 2000. My current, that is a 4 ampere, and my area is equals to 1.6 cross 10 to the power minus 4. So you can say that is called as 8000 multiplied by 1.6. So my magnetic dipole moment is equals to 1.28. You can use another unit that is called as the ampere meter square. Now I want to find it out my torque. So my formula is equals to tau is equals to mb sine theta. My sine 60 or sorry sine 30 is equals to 1 by 2. So I'm putting all those values directly. So my magnetic dipole moment is a 1.28. My magnetic field is a 7.5, 10 to the power minus 2 divided by 2. My torque here I'm receiving over here is called as a 4.8 cross 10 to the power minus 2. Either you can say joule or another unit is called as a Newton into meter. So I have already mentioned you that unit of a torque and potential energy or works are equal, but the thing is that all are not equal quantities, because whenever we will discuss about such type of things, we have to come back to our memory point in 11th science. If a physical quantity contains this unit which is equal, that doesn't mean that these physical quantities are equal. So this is the normal general understanding we had. So now we can have a exercise example number 5.9. And now in this example you have been given that a number of turns of a coil is called as a 16 turns. Your radius over here is equals to again 10 centimeter. Again what I am mentioning is that again, because that they haven't mentioned that it is called as a number of turns per unit length or something. That is why our task is quite easy. Now in the previous example they have just mentioned that area directly, see, but here they haven't mentioned that area directly, so we will just find it out of a circular coil's area. So we will use this area for this one. So my area is equals to pi r square. So I can use this data 3.14 cross 0.1 square. So this is my area which I am supposed to use. Next is that they have given that the magnitude of a magnetic field is equals to 5 cross 10 to the power minus 2 teslas. The coil is free to turn about its axis in a plane perpendicular to the field of direction. When the coil is turned slightly and released, it oscillates about the stable equilibrium from the frequency. Yes, we have seen one theory, and we have been given that that would be 2 second inverse, or you can say that 2 hertz. So we have to find it out. My moment of inertia, I am just using this word I dash, because I have given another I that is called as a current, that is 0.75 amperes. So keep in mind that this is my capital I, which is called as a current 0.75 amperes, and I dash is called as a moment of inertia. It's a short form is called as a MI. So what I'm doing is that first of all I will use this, I am aware about this formula. My F is equals to 1 upon 2 pi under root of MB divided by I dash. So what I will do is that I dash is equals to, I will apply a square on the both these sides, and then my equation would be square root will be removed, and then in the denominator I can have a 4 pi square F square. So now I will find it out my magnetic dipole moments formula, that is sorry, I will find it out my magnetic dipole moment, that is called as M. So I'm using this notation and just finding it out my M, that is called as NIA. My value of a number of turns are 16. My current equals 2.75 and my area 3.14 cross 0.1 square. So my magnetic dipole moment which I have received from this data is 0.377 joule per Tesla. Now I am putting this value in this below expression, and its values are ready to me. So my values as per the notations are magnetic dipole moment is equals to 0.377. My value of a magnetic field is equals to 5 cross 10 to the power minus 2. So I can have a 0.377 multiplied by 5 cross 10 to the power minus 2. I can have a 4 3.14 square, and my frequency is given, that is called as a 2 square, that is called as a 4. So my moment of inertia's value I dash equals to, I can get is that 1.19 or nearest to 2 is called as a 10 to the power minus 4, and the unit of moment of inertia is called as a kilogram meter square. So this is the unit which you have learned in 11th science, but again there is a taste of your units memory, so keep in mind it's a unit as well. So this is quite easy example, but only whenever you are aware about such formula. Instead of this frequency, if I am just asking it you that periodic time, then this equation would be inverse. So at that time our periodic time is called as a reciprocal of frequency. So my formula would be capital T equals to 2 pi under root I dash upon mb in under root. So this is why such type of examples are or theories are very much useful, because it is called as Google equations. So same is the course, same example. By changing these values of electric field or area on something, I can utilize in the terms of periodic time for the electric field and electric dipole moment. So you are aware about the theorem. I have discussed in that theorem concept that instead of M you can place P, that is called as electric dipole moment, and instead of a B you can place that electric field E as well. So your task for the moment of inertia would be quite easy for the chapter number 1.